I'm Professor Yoni Khan. I'm new faculty here. If you've been here for the last couple weeks, you've probably seen me before. So it's my pleasure this week to introduce my theorist colleague, Aida El-Khadra. So we're both particle theorists, and we approach the problems of particle theory quite differently. What Aida does is a fascinating way of understanding the very complicated calculations that go into understanding elementary particles by putting it on a computer and pretending that space and time are broken up into discrete chunks and using that to simplify calculations. So one of the really interesting applications for this so-called lattice field theory is understanding the properties of this particle, the muon, which she'll spend most of her time talking about today. So Professor El-Khadra got her PhD from UCLA. She's been the recipient of the Department of Energy's Outstanding Junior Investigator Award. She's a fellow of the American Physical Society and also a recipient of a Sloan Foundation Fellowship. So I'm really looking forward to learning new things about muons this morning along with all of you. Thanks.
Thank you very much. It's a pleasure to be here, and I'm grateful to all of you for coming out this morning to listen to this lecture. I'm really excited about the muon, and that's what I chose for this lecture. So hopefully you'll be convinced why the muon is interesting. It started its life out very interesting as well. So let me get started with starting with a story, a little bit of history. So we're going to go back to 1934, quite a long time ago, obviously. And we're going to look at the state of the field, the state of physics, particle physics, nuclear physics, subatomic physics, at that time. So at that time, in 1934, roughly, the known fundamental forces were gravity and electromagnetism, and quantum electromagnetism had already been developed and was still being tested, and people were still figuring out how to deal with the quantum theory. Quantum mechanics had already matured somewhat. The known elementary particles, and I put elementary in quotation marks because nowadays we know that not all of these particles are elementary, and I'll come back to that a little bit. So the known elementary particles are the proton, the neutron, the electron and positron, and the photon. So the photon is the quantum of the quantum mediator for electromagnetism. It's the quantum for electric fields and magnetic fields, etc. And electrons, protons, and neutrons we'll revisit in a little bit. So that was the status of as of 1934. It was still a rather rapidly evolving field, and some of these particles had not been discovered so long ago. In particular, the neutron had just been discovered a couple years ago, unambiguously discovered by James Chadwick, and it was previously seen in other experiments, but it was not identified as the neutron, as a particle that lives in the atomic nucleus that is electrically neutral. It was thought to maybe be a heavy photon or perhaps measurement errors, etc. So it had been seen and was later identified by other people that they had in fact seen it and they could verify some of its properties. I have the photos of two women here. Well, first of all, because at this time, well, there aren't so many women that I can put photos up from, and that's kind of important to me. But Marie Curie in particular is one of my heroes. She certainly inspired me when I was in high school to pursue physics. I read the biography that her daughter wrote about her rather several times. So Marie Curie is up here because, well, first of all, radioactivity, and second of all, the source that was used in this experiment was polonium that she named. So it's one of the radioactive elements that, that Marie Curie, together with her husband Pierre Curie, discovered. So that's one of the reasons. Lise Meitner is up here because she also did a lot of studies of the nucleus and then later on also of the neutron, and she discovered fission together with Hahn. But her role in here is that she supplied the first source of polonium to James Chadwick, and he always remembered that. Later on, he received more polonium from other sources, but basically her generously giving polonium to him is how he started this experiment. So what was the significance? Of this discovery here? So in this setup here, what Chadwick found was that this here called unknown radiation was electrically neutral, so it wasn't affected by magnetic or electric fields that you can put there, and that when it interacted with other proton-rich matter, you could knock out protons. And so from the kinematics of all of this, he was able to conclude that this neutral radiation was not a photon, was not a light particle, that it was a heavy particle. It was a particle that was as heavy as the proton, and it was electrically neutral. So prior to this discovery, the theory, the ideas that people had about the atomic nucleus were rather unsatisfactory. We only had the electron and the proton, and to add to what had to be inside the nucleus, the missing ingredients, people thought about maybe the proton and the electron binds in some strange way inside the nucleus. And it didn't make any sense because the electromagnetic interaction that is there is not so strong. There was really no hint of such strong binding. And I'll show this a little bit. So that was a very significant discovery that gave us a much better picture of what the atomic nucleus was like by having the proton there. And then, of course, there's all the applications that, in terms of nuclear physics, that this also inspired. So the other significant discovery was the discovery of the positron. And so this was the first discovery of antimatter, which was predicted, sort of, by Dirac. And in particular, there's a famous story of Rutherford, who had understood the atomic structure of the atom consisting of a small nucleus and an electronic shell. He was rather grumpy about the fact that the positron, that antimatter, basically had been predicted by theorists before they were discovered experimentally. He thought a lot more about experiment than he thought about theory and theorists. So that was a real triumph of the efforts to put together relativity and quantum mechanics in a relativistic description of quantum particles that demanded to have antiparticles there. The other significant piece of this discovery is that it was one of the first discoveries, real discoveries, of cosmic ray physics. So we'll talk about what cosmic rays are, and then I'll tell you a little bit more about the significance of this picture. Now, as with most of these discoveries, there were other people that were working on similar experiments and almost saw or kind of saw those things and realized what they had seen after the fact as well. So there was almost instantaneous, if you want, verification of these discoveries by other people that they could see that this was, that they saw similar results. So what is shown here, this is a track in a cloud chamber of a positron that is being bent. There's a magnetic field around, and so that positron is being bent in this direction. It hits a lead plate and loses energy, and so the loss of energy means that it's bending in the magnetic field more significantly with smaller energy than over here. This track looks exactly the same that a track would look like if it was an electron. The difference is that this track bends this way. An electron that would come in would bend the other way. And that's the discovery of a particle like the electron with similar properties, mass and all other kinematics and charge, but with the sign of the charge being positive instead of negative. Okay, so I'm going to first talk about cloud chambers. Those were an essential tool for discovery. And we have a little cloud chamber demo here. So you can take a look at what's showing up in our cloud chamber here. So cloud chambers allow us to see tracks of energetic charged particles. And right away you can see that there are tracks coming. I mean, we can just look at this for 30 minutes and see things and be excited about the things. This one here is an alpha particle, something that looks like a big fat caterpillar-like thing. Thin, wiggly lines like this are probably electrons. If we see a really long, straight line, that might be something like a muon or a pion. So all of these are hits from charged particles that are hitting the cloud chamber and that are leaving tracks in the room that also pass through all of our bodies at this rate. So there's sort of supersaturated vapor with water and alcohol, and there's dried ice underneath to keep it nice and cool. And then when a charged particle bumps into the molecules, it'll ionize them, and then the ionized trail will cause vapor to condense around it. And so that's when you see these, that's how you can make these tracks visible. Wow, that one is a nice one. Okay, so here's a little bit of a description. So that was one really, really important tool for discovery. And then the other tool was cosmic rays. But before I talk about cosmic rays, I want to have a brief discussion of what happens to a charged particle in a magnetic field, because remember I told you about how there's a magnetic field here that's bending the charged particles. So when you have a charge moving through a magnetic field, it experiences a force, it's called the Lorentz force, that's perpendicular to the direction of the magnetic field and to the direction of travel of the charge. And one often uses the right-hand rule to describe that. And in particular, if the charge is positive, the force goes one way. If the charge is negative, the force will be pointing exactly in the opposite direction. So let me show you another demo for that. So we're going to have to say goodbye to the cloud chamber for a moment, but we'll probably put it up again because it's so much fun. So, okay. So what I have here is just a little cathode ray tube, and it will create a beam of electrons, I think, and we will see the beam as a as a green beam here. So the voltage here controls how fast these move. And I think, let me just check. Yeah, you can see that. So the bending, so these are, it's already moving. So these are charged particles that are just going in a straight line. They're being shot straight out. And when I now put a magnet next, then you can see how the beam is being deflected. If I change the orientation of the magnet, you can see how the orientation of the deflection is exactly reversed. And I can play with that. And again, that's kind of mesmerizing. We can have a lot of fun with that. One of the reasons why I like to do demos, both in these lectures and also in physics lectures, is because I love doing them. Okay, so that's one demo. So that illustrates the reason why. That illustrates how this bends. And here's again an explanation that an electron would have bended the other way, but under the same initial velocity, etc. Otherwise, the track would look the same. Okay, so we have magnets. We have lots of magnets on Earth. In fact, the Earth itself is a giant magnet. And as a result, when there are charged particles coming near the Earth, they do get deflected in Earth's magnetic field. And that can then be seen. Then these particles that get deflected in the magnetic field that spiral in, make light shows like shown here, natural light shows. So let me talk about cosmic rays. These were also called penetrating radiation or Höhenstrahlung, because that was when a lot of physics was still being done in Germany, not for that much longer, unfortunately. And so these are charged particles, very, very high energy charged particles. They mostly consist of protons, but also alpha particles. Remember, alpha particles are also charged particles. Those are pieces of a nucleus that contain 2 protons and 2 neutrons. And so they're heavier, and they can also be heavier nuclei. There can be electrons in there. There can be photons in there. And there's also radiation from the sun. And there is extragalactic and galactic radiation. This cosmic rays coming from supernova, from active galactic nuclei, etc. And their sources are not known. They are some of the highest energy particles that we have observational access to. Some of them, at the various highest energies, the particles are more energetic than what we can make with terrestrial accelerators at the moment. The easiest way to see the cosmic ray particles was by taking balloon flights up. So you would take your cloud chamber and magnet up on a balloon and record these events because the atmosphere will absorb a lot of the cosmic ray particles. So if you really wanted to see a lot, you'd go up on balloons and then bonanza. Okay, so coming back to the status of particle physics at that point. So gravity, quantum electromagnetism, proton, neutron, electron, positron, and photon. And so then the structure was a nucleus with protons and neutrons and electrons in an atomic shell. And I drew this here, this picture. You've seen this many times. You might have built models that look like this, which is sort of like a solar system planetary model looking, where you have the nucleus as the sun and the electrons as the planets. And that looks very nice. And it's completely wrong. So electrons are quantum particles. They are described by a wave function. You can't think of them as little round balls that are whizzing around the atomic nucleus. Instead, it's a better way to think about an electron as a wave function which describes its probability to be found around inside the atom, inside the nucleus. And the electrons, if there are many electrons in here, their wave functions will be overlapping. So the whole thing will look like a fuzzy cloud, kind of like cotton candy. It's not really green. And there will be more structure than what I've indicated here. But the electron wave functions will be overlapping. They're not small, distinct particles that are in the atom. Okay, and if we want to find them, then we have to pretty much destroy the atom if we want to know where they are at any given point in time. So the other thing that's wrong is the scales. The nucleus is way too big. We have to increase the electron cloud, and even that is not quite right. We have to make the nucleus smaller, and even that's not quite right. That's still too large. So the atomic nucleus is much, much smaller than the entire atom is, but almost all of the mass is inside the nucleus. So that's what atoms look like. So this was a little bit of an excursion. This is really not about the muon, but sorry, I can't help myself with this. I don't want to stick with that model of electrons in orbits around the atom. Okay, so that was the understanding, but the nucleus was still rather mysterious. We had protons and neutrons, and what holds them together into this really, really tiny space, whereas the binding of the electron to the nucleus was much weaker, was allowing the electrons to be so much further out. So obviously the force that is keeping the nucleus together is much stronger, and hence it's called the strong force. And so the theory of the nucleus was still something that people were developing. Heisenberg started out with that, and then Yukawa came up with a nuclear theory where he postulated a U particle that would be a mediator of the strong nuclear force. And there were other problems. There was nuclear beta decay, where a nucleus just emits an electron and seemingly nothing else. So those decays violated everything that physicists hold near and dear. Energy conservation, angular momentum conservation, all were violated. So people were discussing how conservation laws maybe were negotiable, quantum mechanics. And it was hard back then to say, well, there could be another particle there that you can't see. That came with a lot of angst, and people thought that, Pauli thought that he did a really bad thing by postulating that. Fermi further developed this into a theory of nuclear beta decay. So what Pauli said is, well, everything would be conserved if there is a particle that is also emitted in this decay that comes along with the electron, and that's the neutrino, and we just can't see it. So with these two, with the U particle as a mediator of the strong interactions, and then perhaps the neutrino for nuclear beta decay, there was a feeling that people were getting really, really close to kind of understanding the universe, understanding everything. There wasn't really much more to be understood. I mean, these people would find out about, and that was probably going to be it. There were some signs of trouble on the horizon. The first observations of charged penetrating particles that were unexpected, that were unexplained, that didn't really make much sense, were recorded, but they weren't always reproducible observations. There could always be some dust in the apparatus or something. So they were a source of confusion, but they weren't really taken as a sign that there was something really, really not understood, something completely new on the horizon. And that is, however, exactly what happened. When this penetrating radiation was studied in a little bit more detail, quite a few groups, Anderson and Nettermeyer, Street and Stevenson, and also Nishima in Japan, were looking at this, and they all agreed that they had seen a new particle. The mass of the particle was, still a little bit uncertain, but it was, somewhere around 200 or so times the mass of the electron. And it was right away interpreted as Yukawa's U particle, and it was named the mesotron, meso for something in between. And, there was something that should be there, that should be the carrier of the mediator of the strong interaction. It's a particle that was seen. Boom, that has to be it. That was wrong. So, experimentation continued. World War II also happened, so this was hard. In wartime Italy, these people here measured the lifetime of this meson or mesotron, and they found a lifetime that was much too long. So this 2 milliseconds, 1 millisecond is 1 millionth of a second, and that was much too long a lifetime. The lifetime should be at least a factor of 100 or so smaller if it was that particle that was mediating the strong force inside the nucleus. The other problem was that these mesons were way too penetrating. The U particle should be something that interacts strongly with the nucleus, so should be able to get absorbed and get captured and scatter strongly when it encounters nuclei. But these mesons were basically saying, yeah, no, there's some stuff here. I don't care. I'm just going to fly right through it, straight through it. And so that's what penetrating means. And so that was also not consistent with this particle to being this mediator of this strong force. So obviously people kept trying things out and were confused. And the idea was floated that perhaps there are two particles, and and sometimes one particle and sometimes the other one is seen. The heavier one would be the mediator of the strong interaction that was later called the pi meson or the pion. And then there was another particle, a muon, that was essentially a heavy electron. In 1947, some 10 years after the first discovery, it was finally in a definite experiment where these gentlemen discovered the pi meson and also recorded how the pi meson decays into a muon, so the lighter particle, which then finally decays into an electron. And here are cloud chamber pictures of that. So here you have a pion that decays into a muon, which then decays into an electron. And you can see that the muon tracks, the intermediate tracks, are all very similar in length, as one would expect. What we now know, of course, is that these decays, that the muon, it's not just the muon decaying, that again would violate everything we hold near and dear, but it's also producing a neutrino that wasn't seen. And similarly, when the muon decays, was also producing, oops, I forgot the anti-muon neutrino in here. Okay. That, of course, goes along for the ride. So that was the situation. So no wonder people were confused. There's two particles, both carry electric charge with similar masses and rather different properties. And I would also like to say, for example, Sakata was working on this and proposing this in Japan during World War II, when Japan was basically cut off. The scientific community in Japan was cut off completely from the US. So a lot of this stuff, a lot of this, these conjectures happened in parallel. People couldn't talk to each other. Always a bad thing, obviously. So once this was all sorted out, Rabi said a famous phrase, "Who ordered that?" People also said, "Oh, this is a 10-year joke." So this was not a friendly exclamation. This was rather, who ordered that? Where does this thing come from? Why do we have to deal with this? It was completely unexpected. There was no reason for it to be there. There was no theoretical motivation for the muon to be there. Complete surprise. It wasn't needed to explain anything. In fact, its existence posed lots of questions, which often new discoveries do. You see the pion and then you have other questions, but at least, okay, the pion is the mediator. The muon wasn't explaining any outstanding questions other than the confusion between it and the pion. There was no real reason for it to exist. So that's the who ordered that. And so that's how we learned about the muon. And you know, it was genuine new physics, something completely new and unexpected. I wanted to come back to the cosmic rays and just to tell you a little bit more about where the muons are coming from. So you have protons and other mostly protons, but also alpha particles, etc. They slam into the atmosphere and break up. They slam into the molecules, atmospheric molecules, and stuff breaks up, and you create some maybe neutrons and pions. And then, as we saw, the pions can decay, for example, into muons. And the muons being very penetrating, they just move through, and then we can see the muons either in balloon experiments, or we can even see them underground. And lots of a shower of lots of other stuff gets created as well, and that's what we were seeing in the cloud chamber as well. Let me turn the cloud chamber back on. Okay, and there it goes. Of course, it was going the whole time, we just didn't see it. So muons are really, wow, look at those. All right, stop being distracted. So muons are really cool. We can, you know, we can use muons as observatories. For example, you can find the moon's cosmic ray shadow through muons. So that's one way in which we can also calibrate your experiment, because we know where the moon is, we know how big it is, we know how dense it is, and so on. And so this is the moon shadow viewed from muons that are observed deep underground in the Sudan 2 experiment in the Sudan mine. So, you know, from complete surprise to calibrating your experiments with. So after that first complete surprise, there were many more particle discoveries that were made in cosmic ray experiments. This is then, not 10. Then also with particle accelerators, that was referred to the particle zoo, a zoo of strongly interacting particles, which we now call hadrons, similar to the proton and neutron, and also cousins to the pions. There was a confusion, there was a very confusing discovery still with cosmic rays, what were then called V particles. It turns out that that was a discovery of a new quantum number called strangeness. Now we call this quantum number is associated with strange quarks, so we know about quark structure, but that was not yet then. The difference between the strong and weak interactions, with which both mess with the nucleus, was better understood. For example, those V particles, which now we know are kaons, were produced in pairs by the strong interaction, but then decayed weakly because because strangeness is something that's conserved in the strong interactions. Neutrinos were also later discovered, etc., etc., etc. And instead of going through all the years, we're going to fast forward to the standard model of particle physics. So we have the electron and the electron neutrino, the up and down quarks, which are which is what protons and neutrons are made of. And that's the first generation, the first family of particles that would have been enough. Thank you very much. That would have been enough to explain what we are made of, everything on Earth, etc. Then, as we discussed, the first second generation particle that was discovered was the muon, and then along came actually a complete set. So there's a charged muon that looks like a heavy electron, there's a heavier version of the neutrino, there's a heavier version of the down quark, and a heavier version of an up quark. And then, more surprises, a third generation was discovered with a yet heavier charged lepton, that's called the tau lepton, yet heavier quarks, B quarks, and top quarks. This beast over here was not discovered until 1996 or so, and is very, very massive, but it was expected. After the muon was discovered and strange quarks was discovered, you were expecting that there would be other stuff. The surprises weren't as big. But then when the third generation particle was discovered again, oh, we have a third one. Do we have a fourth one? Why do we only have 3? And you also heard about the discovery of the Higgs boson, the carriers of the weak force. All of that happened in the intervening decades, and the discovery of the Higgs boson was just a few years ago. So what we have, the standard model of particle physics, is very successful. It describes almost all of our experiments that we do on Earth really, really nicely. There isn't, we haven't really poked very many holes into this, except for that question, who ordered that, which is now turned into, why do we have 3 generations? Why do the 3 generations of particles have the masses that they have? It all started with a muon. The muon was the first particle that nobody ordered. But now we have lots of other rather pressing questions. We know that there is a lot more dark matter in the universe than there is actual matter that we understand very well. We have no clue what that matter is. That's a rather pressing question. We don't really understand what is the mechanism that we end up with a lot more matter than antimatter. To be sure, we're all grateful for that because, you know, existence. But we don't have a good understanding of that. The standard model doesn't seem to provide enough asymmetry to make that happen. There's mysterious dark energy, and there may be new particles that we haven't found yet that might give us clues to resolving some of these questions. And my point is that the muon was the first particle that nobody ordered. Perhaps it can give us some clues to find answers to these questions, dark matter, new particles, etc. And that's what I'll be talking about now, is how to solicit clues from the muon about other particles, what may lie behind the standard model that might give us clues as to the first question that started this. Okay, so in order to discuss that, I want to have a little detour into discussion of a magnetic moment. So we saw in the cathode ray demo that I did that when you have a charge moving through a magnetic field, that the charge gets deflected, gets bent by the magnetic field. Well, the same thing, of course, happens when you put a wire carrying current. What is current? What is what is that? That's moving charges. You can have currents that are made out of electrons inside a metal moving. You can also have currents in liquids and fluids where you have ions moving. But a current is, by electric current, we mean something that's a moving charge. And when we have moving charges in a magnetic field, then these currents experience a force, and the force can move the entire wire or foil back and forth. And there's no good reason for this demo other than that it's really fun. Oh, wait, that's my reason for all my demos. Okay, let's see. So here's your aluminum foil, and that's what we're going to run a current through. And this is obviously a magnet. And so it's providing a magnetic field here, and the current is running this way, either this way or this way. And the current will be generated by music that I'm going to play. So that music creates a current, and when the notes go up and down, current goes back and forth. So you have current going in both directions. And, well, so Yoni, can I ask for you to come up and tell the audience where the sound is coming from?
So it actually is coming from in here. You should come up and convince yourself of that after the lecture, because I don't want to be, just a planted prop. But I've given a little bit of a preview of what might happen here. This is great.
Okay, so it's the vibration of the foil that creates the sound, and the foil vibrates because current is running according to the music. Okay, I'm going to stop this. All right. So that's just to convince you that the entire thing can move around. Now, what happens when we, instead of having, straight wires, when we have when we put the current around in a loop? So this is now a wire loop. Did I forget to turn something off? By the way, this is Erica. She makes all of these demos. Okay. Only this one, right? This one too? Okay. Okay, so I turned stuff on, and now there's a current running through this loop. This is called a Helmholtz coil. And now let's take a look what happens when I put a magnet next to it. Okay, let's take a look what happens. There we go. So what we see is that the coil rotates until it is aligned with the magnet, so that the magnet is sort of pointing, is that the plane of the loop is perpendicular. Let's see. Get that again. There's friction and so on, so it's not perfect. And if I reverse, okay. Well, that's a little bit stronger, I guess. Okay. So what we observe here is that when we put current around in a wire loop, then the loop rotates in the magnetic field. And we can see this here too. Let me. Okay. So the setup that I have here is, this is a magnet, and this is again a little coil. And then I'm going to hook it up to a battery. The battery is out of the screen. The battery is right here. And you can see that it's rotating. Can moving back and forth. It wants to align. Now, if we cheat and if we make it so that one side of the wire is in contact and the other side of the wire is not, then we can turn this into a motor. So, of course, lots and lots of applications to these things. But the point that we want to make here is that the current loop will rotate in a magnetic field to be aligned so that the net torque on the loop ends up being 0. So why does that happen? Because because this little wire loop, you know, each time I run current through a wire, that creates the moving charges create a magnetic field, and that's what causes the forces here. And so running a current through a loop also creates a magnetic field, and in fact it creates a magnetic dipole field that's similar to a bar magnet or compass needle, and that field is characterized by the magnetic moment, which depends on how big the loop is. It depends on how strong the current is, etc. So it depends on the properties of the loop, not on the properties of the magnetic field in which it is placed. Okay. So now we have to add quantum weirdness to the story because we're talking about quantum particles after all. So we just talked about this. We have a magnetic moment when you have a charged particle moving around. Now, the spin of a quantum particle is an intrinsic property, just like the charge of a quantum particle, just like its mass. Those are the things that define the quantum particle, that tell us what kind of a particle it is. So spin is also intrinsic. The spin of a particle is completely independent of how fast the thing is moving, which direction it is moving, how it was created. The spin of that particle is entirely intrinsic and doesn't change. The orientation of the spin does change, but the amount of spin is completely unchanged. Now, the effects of spin are similar to angular momentum. Angular momentum is rotational motion and spinning, like the name says. So the effects of spin are as if the particle was moving, okay, was rotating around. That's what spin, that's the effects of spin, the mathematical, the physical effects of spin. But there is nothing moving. When we talk about an elementary particle, we talk about a particle that's point-like. You can't rotate a point about itself. It doesn't have a size. Even if the elementary particles that we think are elementary are not elementary, if they were, say, composite, still they are so super small that in order to be creating the spin that we see, the motion would be superluminal, much higher than the speed of light. So it's not consistent. Okay. So spin is an intrinsic it's an intrinsic quantity, and it's quantum weirdness. There's no classic analog, but this idea of spin being some sort of intrinsic rotational motion is useful as a picture but we need to understand that it's really not reality. Just like electrons whizzing around is not what the electron around an atom looks like. Okay. So now when we talk about the magnetic moment of elementary particles like the muon or the electron, then we need to know what their spin is. So these have magnetic moments because they have spin. They can also acquire angular momentum if they move around, but they have an intrinsic angular momentum spin 1/2. All electrons, muons, tau leptons, all neutrinos have this spin 1/2. So you combine electric charge and spin, you get a magnetic moment. So we can think of the muon as a little magnetic dipole, and a cartoon picture like that. Now, because of this intrinsic spin, when you put the muon into a magnetic field, it will precess about the direction of the field, pretty similar to how a top spins when it goes a little bit off axis and it kind of wobbles and then stops because friction. Let me try this one. Okay, it's supposed to be staying there and moving the other way, but you get the idea. Okay, I have another toy there that is a little bit harder to get to work that I will, okay, I don't want to step on these things. So the muon magnetic moment, thinking about it like a spinning top, that it is precessing when placed into a magnetic field, is a nice analogy. So we need to add a little bit more quantum weirdness here. We're not done, sorry. More quantum weirdness, we have virtual particles. So we think of vacuum going out into, deep space, empty space, nothing there. True, but not really empty. Not really no energy there. So by the uncertainty principle in quantum mechanics, it is possible to use a little bit of energy to create particles out of that energy for a fleeting moment. And all particles that exist can do that. So those particles are called virtual. So they can exist by the uncertainty principle. The time by which they can exist is shorter if you have to violate energy conservation for longer, and so that's what controls their existence. Virtual particles in the quantum world affect all processes, including how a muon interacts with a magnetic field. So the magnetic field, we talked about the magnetic field, the quantum of the magnetic field being a photon, which we often depict by a wavy line that we have here. So we don't have a point-like particle interacting with a magnetic field because there's a cloud of virtual particles that affect how the muon interacts with the magnetic field. And that cloud of virtual particles, those are quantum effects. So this particular interaction is rather sensitive to the presence of these virtual particles. So all particles that we know about, they can contribute to these virtual effects. And these effects can be calculated with the theories that we have. The quantum field theories that make up the standard model, which I didn't really talk about here. Okay, now, this was done very, very early on. The magnetic moment of the electron was measured. It was found that it deviated from the expectation that you would have if it was a point-like particle, if there was no virtual particles contributing. And Schwinger is the one who did the calculation of the first virtual correction, where you have a virtual photon. And lo and behold, the two agreed. So this was a very important step in understanding and and verifying that quantum electrodynamics, that weird marriage between quantum mechanics and relativity, is actually really a real theory that makes real predictions that can give us precise theory predictions that can be confronted with very precise experimental measurements. So it's such a crowning achievement that it's encarved in his tombstone. The alpha over 2 pi is this number, and so that was very important. But coming back to the, oops. So coming back to the standard model, this is the state of the art of the virtual corrections that have been calculated. So all of the standard model contributions contribute, and some of the virtual corrections in QED have been calculated to many, many orders in perturbation theory. Okay. So everything from the standard model contributes. Any other particles which we have not yet observed, obviously, can also contribute virtual effects here. For example, particles that are connected to that elusive dark matter. So if these particles contribute to the muon magnetic moment in a significant enough fashion, then when we measure the magnetic moment, that measurement will disagree with standard model theory. So that's one way in which we can hunt for new particles, by making comparisons between precise experiments and precision theoretical calculations. So these kinds of tests, these kinds of looking for, trying to understand what new particles there may be, they don't depend on what you might assume for what these particles are in order to hunt for them, but they do depend on people being able to make precision measurements, which check, and precision theoretical calculations. So why is this particularly interesting? Well, because there is a disagreement that is over 10 years old by now. Unfortunately, that disagreement between theory and experiment is not at the level of significance where we can say, aha, we have found new particles. We know for sure that this difference cannot be explained by a statistical fluctuation or somebody slightly underestimating the errors or something like that. So the significance has to be larger. The significance of the difference has to be more than 5 standard deviations, where the probability that you're dealing with a statistical fluctuation or just plain bad luck is essentially 0. It's 0.0000 something percent. So at this level, the probability that this is just a fluke is already rather small. It's much less than 0.1%. So that makes it interesting, but not yet at the level where we can claim victory. So what is happening, and that was on my slide, on my title slide, is there's an experiment being mounted at Fermilab in our neighborhood, so to speak, up north near Chicago, which aims to reduce the experimental measurement error for the anomalous magnetic moment by a factor of 4. At the same time, there is a theoretical effort going on, including the kinds of calculations that I do, but also lots of other tools to do the standard model theory redundantly with different methods, with different methodologies, with different errors, so that we can be sure that the standard model prediction is what we say it is. So it's a rather serious effort as well. And if we're lucky, then at the end, we will see something like a 7 or 8 standard deviation significance in the difference, which would be victory. If we're not lucky, then we will learn a lot about what the possibilities are for new physics, or basically what the possibilities are for new physics where they are not. So this will give us very strong constraints, but it's a lot more fun if you actually see something, if you can claim discovery, obviously. So let me just move to the summary and the outlook. As I think a point I made is the discovery of the muon was absolutely a complete surprise, such a surprise that it was misinterpreted for 10 years. Now we've been having 10 years of tension that is not big enough and not, it's tantalizing. It's the most significant tension we have, but not yet quite significant. We don't have an answer to that original question, who ordered that, or the modern version, why are there 3 generations, and why do they have their masses, etc. However, the muon will soon provide us with answers to other outstanding problems in particle physics, which may in turn lead us back to being able to answering those fundamental questions. And to me, that is a very exciting prospect. Thank you for your attention.
Okay, we have time for a couple questions. Yes?
What do you think the chances of finding a 4th generation?
So there are quite a lot of constraints coming from high-energy experiments. In particular, there was a series of experiments that were performed both in Geneva, where electron and positrons were accelerated and collided together to create Z bosons. And the Z boson would then be able to decay into all the particles, including 4th generation fermions, if those 4th generation fermions are light enough. So we know that if they exist, they would have to be rather heavier. So the bounds on 4th generation fermions are rather severe, that it doesn't look very likely. But we're always just guessing, right? So, yeah. I tend to take an agnostic view on this, but one has to take the existing information seriously. Yeah.
Is there any way to create muons besides the decay from something else? Is there a way to build up?
Is there a way to build up?
Well, reversing the muon to electron path. Is that possible?
Can you create muons in some experiment?
The way that people create muons is from smashing protons into stuff, creating pions, and the pions decay. You can create muons the other way around. You can, for example, in the experiment I described, you can take electrons and positrons and smash them together and create pairs of muons from that. You can do that in other high-energy collisions, and people do that as well.
Maybe I'll also mention that you can, so if you have enough muon neutrinos, you can use muon neutrinos to make muons by bumping them into a nucleus and kind of reversing that decay process.
Indeed, that's how neutrinos were discovered, but then you have to have muon neutrinos, which come from...
Right, yeah, the problem is it's very hard to get enough neutrinos, and they're not charged, so you can't manipulate them with a magnet and stuff like that. So it happens, but pretty rarely. More questions?
How do you measure how much anti-gravity or dark energy or any of that stuff? How do you measure it?
So,
More or less?
dark matter and dark energy?
Yeah, or antimatter, you know.
Okay, so antimatter is the very simple observation that everywhere we look in the universe, what we see is matter. It's the luminous matter has matter properties, not antimatter properties. If there was antimatter, there would be a characteristic in the border between where you have matter and antimatter. There would be annihilation that we would see. We don't see that. Because matter and antimatter can annihilate.
So how do you know there's antimatter then?
I'm sorry?
How do you know that there is antimatter if that's the case?
Well, we know that the universe consists mostly of matter. Energy can be turned into matter-antimatter particles. So we can create antimatter particles, and through other collisions, we will have antimatter particles, but they are a much smaller, composition of the entire universe. If they
How
were,
are you detecting the antimatter? What is the antimatter doing that makes you know? That
well,
it's
one way is through annihilation into photons, say. Matter-antimatter annihilation. So to answer your other questions, dark matter and dark energy are cosmological observations. So we know, I mean, there's a whole bunch of observations, but the first hint we had for dark matter was looking at what are called rotation curves of galaxies. How is a galaxy, what is the rotation of a galaxy? We can measure the velocities of the stars, the velocity distribution from the center all the way out, and those velocity distributions did not match with, if you have a certain amount of matter, if you have a matter distribution, then by Newton's law, you know how fast things have to go as you go out, because, Newton's law is keeping this together and keeping this rotating. So those did not match, and match by a lot. And so a reasonable possible explanation is that there is in fact a dark matter halo, that there is a lot more unseen matter in the galaxy, a lot more unseen matter than there is visible matter that you can count, that you can know how, the stars, how big they are, how much mass is in the stars, you count them all up through the luminosity. So there had to be all this matter there that was dark. You can also think about modifying Newton's gravity to account for that, but you run into other problems and other issues with that. So that was the first hint for dark matter, but we have lots of other cosmological observations as well, and they all tell us the same thing. So it's not just one thing, but it's a whole consistent set of observations. That doesn't tell us anything about what that dark matter is, and probably not just one kind of particle, what the particle nature is. We have absolutely no clue. So we've looked for dark matter, we've tried to produce it, we've tried to scatter it and look for signals, and we haven't seen anything yet. Yoni is one of the people who comes up with amazing, new, beautiful ideas for how to look for dark matter, and it would be wonderful if, some of the experiments that he thinks about and designs, bear fruit in that. But we don't know what the masses of these particles are. We don't know how they interact. We don't know how many there are, how they interact. So we pretty much have to look everywhere to do that, including there may be a signal in dark matter in the muon. Dark energy is related to how the universe is expanding. So it was the observation that the expansion of the universe, the rate of expansion, is increasing, and that is because there's this. So the way to think about that is that there's this, again, unseen dark energy that is pushing things apart faster than we were expecting. So that's one way to think about it. There's other more theoretical ways to think about it. Okay? Yeah.
Sweet. I just want to ask you one question while you're up here. So if you have to bet money on there being a discrepancy, I have a bet on this, so I've already put my money down. How much money would you bet that the experiment at Fermilab will find a value that's discrepant with the theory results that you and your colleagues calculate?
There's a camera here. I'm going to go with $100.
That is actually more aggressive than me, so that's great. I mean, yeah.
And with a yes.
Yeah. No, I think, yeah, if they find a result that's
So is that
discovered.
our private bet? Do I owe you $100?
No. I don't even, yeah. I'm not sure if
I owe
I.
Tony $100.
Yeah. So maybe in the interest of time, let's thank Professor El-Khadra again. And are you going to stick around for a few minutes to answer questions?
I'm happy to answer questions if people want to play with some of the demos. You know, Erica will make sure that nothing gets destroyed. And please also give a big round of applause again to Erica, who set up all the demos.